welcome back. This is going to be the second episode in our predictive analytics series. This is Hard Math with Kevin. I'm here with Kevin Mabe, the Chief Analytics Officer for Chorus. So Kevin, in the last episode, you showed us a little bit about why you want to have holdout data and why you want the model data to fit the holdout data within predictive analytics testing. What are we going to look at today?
So today we're going to discuss categorical variables. So when we're trying to predict things like segment or decile or things of that sort, where you're not predicting a thing like a height, you're predicting customer segment 1, customer segment 2, customer segment 3. And what we're going to do is kind of go through how to further evaluate the robustness and the fit of your model when you have a situation like that. So I'm going to show you a lot of numbers now. This is what's called a confusion matrix. And so a confusion matrix is...
aptly named.
Yes, aptly named, exactly. So a confusion matrix is essentially an n by n table of how the model fit the actual segments, and in this case it's 1, 2, 3, with the predicted segment of 1, 2, and 3. Now, just to kind of give an overall view, this example used 60% of the original data set. So what you're seeing here is how the model performed on the actual segments here, 1, 2, and 3. So one major thing that is great about such a confusion matrix is I don't really care about the algorithm that got me to this point. This is an algorithm and methodology agnostic way of looking about how a model performs. And so let me kind of go through what we see here. So first of all, you see for the actual segment 1, 2, and 3, here's the totals. So there was about 82,000 data points in this set. Customer segment number 3 only had about 5,700 actual people.
Kevin, just before you continue here, you said 82,000 data points. Is there a number that you need to get to in order to find that you have a robust predictive model? Obviously, 82,000 seems like a lot, but is that not a lot?
No, it's quite a lot. The age-old question of how much data do I need in order to build a good model really depends on the type of signals that you have available to even describe or predict the observations. And so that's a long way of basically saying you can build a predictive model using 100 data points or 200 or 2,000. And if the signals are strong enough in your model, then it will overcome the fact that you have fewer and fewer observations. This was a larger study, and so therefore we took great advantage of a much more complex model for these 82,000, but there's no real magic number regarding that fact.
Right, okay.
So customer segment 2 is the largest group here, 48,000. And then customer segment 1, there were 28,000 here. So what this n by n, or basically 3 by 3, basically says, in segment 1, for the actual segment 1 members, which is 28,000, how many were predicted as 1s, how many were predicted as 2, and how many were predicted as 3. And so you'll see that 16,000 were in fact correctly predicted as 1s, 12,000 were incorrectly predicted as 2, and about 190 were incorrectly predicted as 3. And so the sensitivity or the accuracy of segment 1 is about 57%, and we got that basically dividing 16,000 divided by 28,000. And if you take a look here, you'll see that the accuracy differs quite a bit amongst customer segments. So the most accurate segment was segment 2, where 42,000 of the 48,000 were correctly predicted as 2, with some incorrect predictions here and here. And the same thing for segment 3, the accuracy was 40%. This is actually not the way that we look at the predictivity of these segments. So one overarching metric is called the hit rate. Basically, how many were correctly predicted. So what that is that's the sum of the actual 1s predicted as 1s, the sum of the actual 2s predicted as 2s, and the actual 3s predicted as 3s. So the 16,000 plus 42,000 plus about 2,200 divided by 81,000 is 74%. So Drew, is 74% high or low? Is that a good hit rate? I'm
guessing here, but that seems high.
Okay.
Seems good.
So it seems good, but unfortunately, what you don't know is context. So you don't know whether that 74% is high or low because there's nothing to ground it on. Well, if we were to employ a monkey and that monkey built a predictive model, his best option is to predict everyone as a segment 2. Why? Because that's the largest segment that we have in the group. So a monkey would be able to predict 48,000 correct out of 82,000, right? So let's use my handy-dandy calculator here to figure out what that means. So a monkey can get a hit rate of about 59%. So now you see that the baseline that we would have to beat in order for this to even be called predictive, it has to beat 59% on an overall basis. And so this hit rate of 74% actually is pretty high. And what that means is that we were able to beat a monkey, but we're basically able to beat that 59%. And the model just demonstrates here how it does a better performance. There is a metric called an adjusted count R squared, which basically says how much better than a monkey did I do. And so for this model, that metric is 36%, which is actually pretty high. So we're calling that a moderately predictive. And what that 36% is the distance between that 59% and 100 compared to the distance of 74% and 100 measures about 36%. We've closed the predictive error by 36%. So this is actually a pretty solid predictive model overall. Does that make sense, Drew?
It does. Yeah, that's actually very helpful.
And the reason why this is a big deal is because sometimes you'll take medical tests where it's 98% accurate, but the problem is it's testing for very low incidence diseases. And so you can build a predictive model using that test by just presuming that no one has the disease and be 97.5% correct. So to tout a 98% accuracy just doesn't make sense until you give context for what is the largest category that you're actually predicting. There's another thing.
Really interesting.
There's another thing I want to point out here. Most of academia and many predictive modelers will report these accuracies by actual segment. We note them, but we really don't care about that. And why? Because we're actually interested in a predictive model. We do not have the luxury for incoming data what the actual category is. We only have the predictions. So what we look at are called the predictive values for each segment. So for instance, for those that are predicted 1, how many were actually segment 1? And that answer is 74%. How many of the predicted 2s were actually 2s? That's 74%. How many of the predicted 3s were actually 3s? That's 67%. Now the reason why this is helpful is because you can see where there could be some potential bias and where the model does a better job of predicting and where it does a lesser job. The other good thing about this is, for medical tests, for instance, going back to medical tests, you're not interested in how many actual disease were caught. You're interested in your own blood sample. And so if you get a positive result, you want to know from an overall standpoint, given that the test was predicted positive, what is the likelihood that you actually have the disease? And that's when you're talking about the predictive values here, is because the only thing you have the luxury of is the predictions, and you want to understand how they fit. So going forward from this is just for the model data. And what I'm going to do is show you the same table for the holdout data. Now it's a little bit smaller here. And I'm not going to go into too much detail, but the point is this, is that when you're building a model with a holdout, here's the holdout data sample of 40%, I also can build this confusion matrix, and I should expect and statistically test that whatever I see here in terms of all of these metrics and values, I should see here from a statistically similar manner. If not, then I need to go back and rebuild the model or leave out some variables or make sure that I'm not fitting noise in order to get to this point. So not only do I understand the predictions versus actual the model data, but I want to impose that the holdout should look the same way. The model's performance on the holdout should look the same way. And if I see some statistical differences in how this 3x3 looks from model data to the holdout data, then I need to keep going with my analysis to come up with something that's much more robust.
Excellent.
Awesome, Drew.
Well, yeah, Kevin, as always, thank you. And we've got one more in this series going forward, so we'll have that up here within the next week or so. But thank you as always.
Yeah, thanks again, Drew.